So it is from a joint work with the Pramod Uni and Shaoligun, and it concerns the local distribution of the product of two shifted primes, and there is some application which was indeed some our motivation. Okay, so let me start like that. When we consider a sequence of integers, that is to say increasing sequence of positive integers, and the counting function is just to count the number of elements up to some x, real x, and from that you have some idea whether your sequence is rich or not by considering the quotient a of x divided by x, and you take either the lim sup or the lim inf, and those are densities, asymptotic densities, and if they exist, this is called the asymptotic density. For example, prime number have a zero asymptotic density because the counting function is something which is little o of x, and an arithmetic progression has an asymptotic density, which is the inverse of its difference. Okay, interesting sequence is that the following. We take the union of small intervals around 2 to the n. We take all the integers between 2 to the n plus 1 and 2 to the n plus 2. The bracket we have here means the integers in this real interval. And this sequence is very thin because up to x, the number of elements is log x squared. You see, you take only log x values of n, and each time you have a value of n, you have n terms, and so you have something which is log n squared. But it has some interest in that it contains arbitrarily large subintervals. So on the local distribution, it can be locally very rich. And there is a way to measure that, which is called we call it here the Banach density. It is either the upper Banach density or the upper uniform density. We'll say only the Banach density. You do the following. Around x, you count the number of elements between x and x plus L. You divide by L, and then you take the lim sup of this quantity, and then you take the limit when L is tending to infinity. It's a good exercise for your undergraduate student to show that the limit indeed exists. On that. For example, if you consider the U sequence, which was defined above at the beginning of the slide, this density, the Banach density, is 1. So it is very thin. U of x is big O of log x squared, but it has the maximal Banach density because locally it is very rich. Okay. Now, for example, this is an exercise. I'll give you some hint about that. The set of prime numbers has Banach density 0. So it is not that poor sequence, but it has asymptotic density 0, but it has also Banach density 0. You cannot have big clusters of prime numbers. If you want to know how it goes, you take the following. You take if you consider an integer m, the number of primes in an interval between x and x plus m, when x is large enough, it is at most phi of m. And phi of m because the element, the prime number has to be co-prime with m. And so one has phi of m over m. It's known to be the product when the prime number phi p divides m of 1 minus 1 over p. And as you know, the sum from Euler, we know that the sum of the inverse of the prime number is divergent. And so this phi of m over m can be very small, as small as you wish. So you do the following. You take some epsilon positive, and you choose some m for which phi of m over m is at most epsilon. Now, if L is larger than m squared, or whatever you wish, you don't have that many primes between x and x plus L. Essentially, you take number of intervals which are multiple, which are just of length m, and in those you have something which is epsilon term, so you have epsilon m term, so you have epsilon L, and plus something which is 2m. And so this is at most 3 epsilon L. And so you see that the Banach density is 0, less than 3 times epsilon or whatever. It's nice also to notice that if you take the number of positive, the set of positive integers with at most L distinct prime factors, it has also a Banach density 0. It is richer, but still it has Banach density 0. You not have cluster of them. And again, the proof is by, not again, but the proof is by induction on the number of prime factors. Well, how does it work for 2 primes? Well, we keep our favorite m, for which phi of m over m is at most epsilon. And now we consider the product of 2 primes. We may assume that q is the smallest of them. Now, if either qr is coprime to m or q is at most m. Now, if the elements which are coprime to m has Banach density, which is at most epsilon, as we saw before, and so by the same argument, and so the set of the numbers qr with q less than n is a finite number of dilates of p, and this is easy to see that if you take the union of different sets which have 0 Banach density, then they have also 0 Banach density. So, okay, this is the point here. So now we may enter, with time we enter the game, and where is it? It's here. Okay, now we look at shifted primes. So you take q, which is p minus 1, when p is a prime number. Of course, this set q is a translate of the prime number, and again, for the density, it doesn't change much. You can see that you don't have clusters of element p minus 1, otherwise you would have clusters of element p themselves. So the set q has 0 Banach density, and now the point is to know what about the product. We saw that the product of primes have 0 Banach density, but the product of shifted primes may have a very different structure. Of course, you see QR. Well, the 1 here is not a problem, but you have Q plus R also, and this may change completely the picture. Okay, so the question we want to tackle is what is the Banach density of Q2? Can we find some clusters there? And the answers we gave with Eyuni and Gun, Pramod and Shaoli is the following. We unfortunately we have no unconditional result. So if we use a classical conjecture of Dixon, then the Banach density of Q2 is 1 over 6. So let me tell you what is Dixon's conjecture. So Dixon conjecture says the following: if you have S polynomial of first degree 1, with integral coefficient and positive leading coefficient, such that the product has no fixed prime divisor, then you can find integer t for which f1 of t blah 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 fs of t are all prime. So fixed divisor means that when you are looking at the product f1 of n and f2 of n, fs of n, then when n runs through n, sorry, I was unmuting. It seems that now it's fine. Otherwise, you please do something to tell me. I don't hear anything, but you can solve that problem. Okay, so it means that the product has no fixed prime. So to take some example, if you take simply x plus 1, then x plus 1 is always an even number. When x is an integer, it is always even. And so you don't expect to have infinitely many primes so that p plus 1 is a prime number. However, if you take x and x plus 2, they have no fixed prime divisor, and so you may expect, and Dixon tells you this would be the case, you have infinitely many primes such that p plus 2 is also a prime. So you see Dixon implies the Dixon conjecture implies the twin prime conjecture. Okay. By the way, the only case when Dixon's conjecture is known is when S is equal to 1. That is to say, you have only one polynomial ax plus b, and to say that it has no fixed prime divisor, it means simply that a and b are co-prime, and then this is Dirichlet theory. Okay? So otherwise, we don't know anything about that. Okay. Now let us go on with this here. To go to the next slide. Yeah, done. So first of all, the upper bound. You see, we want to show that the Banach density of Q2 is equal to 1/6. The upper bound is easy. The set of elements Q minus 1, R minus 1, where one of the primes Q and R is 2 or 3. This is the union of two dilates of Q. And so it has 0 Banach density. And otherwise, if Q and R are different from 2 and 3, then the number you have is congruent to 0 or 4 or 12. And so this is why you have a density which is at 1/6. Okay? The lower bound, this is the question. So from now on, you take h, the given positive integer, capital H, and little h will run in the interval 1h. So what we want to do, what we do now is always under Dixon's conjecture. Maybe I don't repeat it all the time, but what we want to show is indeed even more than the Banach density, is to find consecutive elements which are congruent to 0 or 4 or 12, and which are the product of two shifted primes. So what we have is what is written here. We want to say that m plus 12h is q minus h r minus qh minus 1 rh minus 1, and the same for m plus 12h plus 4, and for any h between 1 and capital H. And this will give you the Banach density 1/6 anyway. Now, to present the proof, I will present something which is a simpler version, which is just to consider the case, the first case, m plus 12h is qh minus 1, rh minus 1. Be careful, it's not enough to do it independently for m plus 12h and m plus 12h plus 4. You have to do it at the same time, because it may turn out that one Banach density is okay, it's 112, and the other one is 112, but the interval in which you find someone are not the same one. So it's not half of the proof, but it's not too complicated. It's just technically more complicated to fit. So this is what we want to do. Okay. So what we want to do is to construct a family of primes Rh and integers a and b, capital A and b, so that we can apply Dixon's conjecture to the family of polynomial fht, which are at plus b plus 12h divided by rh minus 1 plus 1. Because you see, if those numbers are prime numbers, say fh of t is qh, then you have written at plus b plus 12h is qh minus 1 times rh minus 1. And so your m will be the at plus b, for the t you have found through Dixon's conjecture, and you have exactly what we wish. Okay? So now the point is that you see that we have to have some condition that we can apply Dixon, that is a polynomial with integral coefficient, and it will be easier to make our life easier. We may assume that Rh minus 1/2 is a prime number. Well, again, you see, this is, if it is a prime pH, it means that 2pH plus 1 is a prime, Rh, and this is a Sophie-Germain prime. And again, it is something like the twin prime conjecture, and Dixon conjecture will be very nice to show you that it is possible to get that. Since anyhow we are going to use Dixon, we can use it at that step, although it is not necessary. We can manage by using sieve and saying Rh minus 1 as at most 3 prime factors or something like that, and be in a good position. Okay. So we use this, and so what you write simply fh of t is 8 plus b plus 12h divided by 2ph plus 1. So we need to have some conditions for pH, so that all that is fine. I prefer to give them first. It is, well, I just write it like that. We need to have something. We take all the primes. Well, pH is such that the GCD of 6H plus pH and P and 6K minus H plus pH by 2 is co-prime with also with this number. And the proof is just by induction. Well, of course, what we are doing is to find sufficient primes. This is just Dixon conjecture, but we need also to put them in a good arithmetic progression. So we have to be a bit careful about that. But this condition is not really very strong, because what we are saying is that we are excluding some congruence classes. We want just the GCD. So this is not too difficult to do. I mean, this is technical, but we can completely skip it. Okay, now we define A, B, and the polynomial FH. So PH will be the product of the prime, all the primes of 2 capital H. A is 6 times PH times the product of the PH we have introduced in the previous lemma square. And B is congruent to 0 mod 6 PH and minus 12 mod PH square. And this is not a problem, because those two elements are co-prime, and the different pH are co-prime by themselves, and so you can solve this, and there is no difficulty with that. And now we construct FH, which is AT plus B plus 12H divided by 2H plus 1. So maybe we can try to see why this polynomial has integral coefficients. So first of all, with respect to 2, we see that A is divisible by 4. Remember, there's this extra factor 2, there's a factor 2 here, and there's a factor 2 in pH, in 6 and 1 in pH. So it's fine. This A, B also is congruent to 0 mod 6 pH, and so it is divisible by 4, and 12H also. So all that is divisible by 2. And by the way, you can notice also at the same time that in the numerator, you keep a factor 2, and it means that FH of T is always odd. So this would be fine for Dixon. We are happy to have something which is always odd. What about pH? Again, pH is a factor of A, pH is a factor of B. B plus 12H is divisible by pH, and so this is a polynomial with integral coefficients. Now, what happens for the different prime factors? So it is integral coefficient, and we have to enter now into the Dixon business. I don't know what is the best, if it is to see it written here, or to go back to this and just to wave hand. What about, now we want to know what are the different possible coefficients. You see, if a prime number is larger than A, is larger than capital H and different from PH, then you are happy, because it doesn't divide A, and this polynomial fh of T is not 0 modulo P. It has integral coefficient, and if it is not 0, it has at most H zeros. Okay? And so it cannot be divisible. Well, the product of the FH is, product of the FH is as a degree which is capital H, and so if you take a prime number for which this polynomial is not a constant, that is to say the coefficient of T is strictly positive, then it has at most H solution, and so your T is not a fixed prime. So the only fixed prime may be the one which are less than capital H and the pH themselves. So for the one which are less than P, we did everything so that it works well, because P divides A, P divides P plus 12H, and so since you are P divides the numerator, and so you are happy divides the first part, and since you add 1, it is co-prime with capital P. For the pH, okay, pH, fine. For FH of T, it's fine if it is not a divisor of FH of T, but it may be the divisor, just because, again, A is divisible by pH, and B plus 12h is divisible by pH square. And so all that is divisible by pH, and you have something which is a multiple of pH plus 1. So you are happy. But the point is that pH may be a divisor of K. So this is the only, let us say, a bit the point to see at. Okay? So this we don't need that. This is what I was saying by waving hands. Now, as we consider Fk not pH, okay? As above, pH divides Fk of T if and only if it divides At plus B plus 12K plus 2pK. But, oh well, Wolfgang, thank you for having changed so quickly my slides, because there was a mistake in the first one. Okay, so what we know is that At plus B plus 12H is divisible by pH. So pH will divide At plus B plus 12K plus 2K if only it divides 6K minus H plus pK. And you remember, to show that in our construction, we said that pH is co-prime with 6K minus H plus pK. So we are happy. This is why we put this on this. So we can apply Dixon's conjecture to our set of polynomials, and so we proved in that way the lower bound 1 over 12 for the Banach density of Q2, and of course, just with technically slightly more complicated construction, you can prove that the Banach density is 1 over 6. Okay, so now we go to the application, which was indeed our motivation with Pramod and Shaoli. It comes from a point that has been studied by Mithun Kumar Das, Pramod Deshouillers, our collaborator, and Bhuvanesh Rao Patil. And they looked at the Banach density of the set V of the values of Euler's quotient function. And they had some argument which was not that clear, suggesting that the density should be 0. And of course, we know already from now on that this density is at least 1/6, because the product of two shifted prime is a value of Euler's function. And there was a theorem last millennium by Ford, Konierging, and Pomerance saying that the Banach density of the set V is at most 1/4. What they prove indeed is that essentially, first of all, we know that 1/2 is trivial because the values of the phi function are essentially odd or even, except phi of 1, which is phi of 2, which is 1. And all the other values are even. Now, as soon as you have two prime numbers, two prime factors, odd prime factors, then phi is divisible by 4. Now, what may happen is that you have one prime only, but then if it is a prime factor, it may be a prime power. This is the only case in which you have something which may be different from how to say, not divisible by 4, but being even. And this is very seldom, and this is what they prove. They proved a lot about those things by the way in the paper, but essentially they showed that the number of congruences for which phi of is in those congruences of 4 is very, very, very limited. And this is the way you get this upper bound. Okay, it's sophisticated, but it is higher. And so what we proved with Pramod and Shaoli is that under distance conjecture, one has this lower bound. So we have to do something which is a bit better than the 1/4. So you see with the values we have r minus 1, q minus 1. We can go to the value 1/6. We can do slightly better, but as soon as we put 3 odd distinct primes, then we obtain the number we have always divisible by 8. And so this problem is to cover the congruent class 8 mod 24, but not the class 20 mod 24. So we have done a bit better, a little step further by the same argument. And this is not enough, and so what we did is to consider numbers of the shape r minus 1 r cubed, q minus 1. So we see it is divisible by 4, but not by 8. And this is the value of the phi function. It is phi of r to the 4 times q. Okay, so it is more technical, but the ID, the basic ID, we already showed. So it's fine. You can replace r cubed by r simply, but then there is some little difficulty with the prime 5, and it turns out that this is better to put phi of r4 times q. Okay, so this is what we have. And so we proved indeed more than the Banach density. We showed that over distance conjecture, we can find an integral m such that around n on the length as large as you wish, on well, n depending also on the large you wish. But all the multiple of 4 are values of Euler's function. Okay, now the difficulty here is that unfortunately we have no idea how to prove that the set of the values of Euler's function has a positive orthogonal density. So it would be nice to have something like that. And we looked at this, no idea, and would be really very happy if someone could help us with this question. So, okay, thank you very much for your attention. And yeah, no, this is. Yeah, I go backwards. This is not backwards. This is forward. Okay, thank you very much. So maybe the organizer, you can put me back on the hearing what is going on. Thank you.